Easy come for you. Discovery of the nucleus by Rutherford's alpha ray experiment. Hello, students. Welcome to today's lesson on one of the most groundbreaking discoveries in chemistry, the nucleus of an atom. This discovery, made by Ernest Rutherford in 1911, changed our understanding of atomic structure forever. Let's dive in and uncover the story of the famous gold foil experiment. Before Rutherford's experiment, the widely accepted model of the atom was the plum pudding model proposed by J.J. Thomson. According to this model, atoms consisted of a positively charged pudding with negatively charged electrons embedded within it, much like raisins in a pudding. But Rutherford had a different question in mind. How is the positive charge distributed in an atom? To test the structure of the atom, Rutherford and his team, including Geiger and Marsden, conducted a series of experiments using a beam of alpha particles. Here's how the experiment was set up. Rutherford's experiment relied on alpha particles, a type of radiation discovered during the study of radioactivity. Radioactivity is the process by which unstable atomic nuclei release energy in the form of radiation. Alpha particles, which are positively charged and consist of two protons and two neutrons, are emitted during nuclear decay of elements like uranium and radium. These high-energy particles became Rutherford's probe to investigate the structure of the atom. To test the plum pudding model, Rutherford and his team designed a precise experiment. Let's break down the components. 1. Alpha particle source. A radioactive material, such as radium, was used to emit a beam of alpha particles. 2. Collimator. A narrow slit ensured the alpha particles formed a fine, focused beam. 3. Gold foil. Thin sheet of gold, just a few atoms thick, served as the target. Gold was chosen because it is highly malleable, allowing alpha particles to pass through. 4. Detection screen. Circular screen coated with zinc sulfide surrounded the gold foil. When alpha particles struck the screen, tiny flashes of light were produced, marking their impact points. In the alpha ray experiment, thin gold metal foil was bombarded with alpha radiation from radioactive substances such as radium, and Rutherford observed something astonishing. 1. Most alpha particles pass straight through the gold foil without any deflection. 2. A small fraction of particles were deflected at small angles. 3. A very tiny number bounced back at large angles, almost as if they had hit something solid. Rutherford described this surprising result as if you had fired a 15-inch shell at a piece of tissue paper, and it bounced back. Based on these results, Rutherford concluded that 1. The atom is mostly empty space, which is why most alpha particles pass through. 2. There is a small, dense, positively charged region at the center of the atom, which he called the nucleus, causing some alpha particles to deflect or bounce back. This led to the nuclear model of the atom, where electrons orbit a central nucleus, much like planets orbiting the Sun. Rutherford's model revolutionized atomic theory, but it had limitations. Advantage: it provided the first clear evidence of the nucleus and the idea of atomic structure. Limitation: it couldn't explain the stability of electrons in orbit around the nucleus or atomic spectra. These questions were later addressed by Niels Bohr. Now, let's test your understanding. Try solving these questions. What observation from Rutherford's experiment led to the conclusion that atoms are mostly empty space? Most of the alpha particles pass through the gold foil without any deflection. This observation indicated that atoms consist largely of empty space, allowing the particles to pass through undeflected. If most alpha particles pass through the gold foil without deflection, what does this tell you about the distribution of positive charge in the atom? The lack of deflection for most alpha particles shows that the positive charge in an atom is not spread out evenly, as suggested by the plum pudding model. Instead, it is concentrated in a very small, dense region, the nucleus. Instead of being drawn to the center nucleus, why did the alpha particles deflect away from it? Alpha particles are positively charged, and the nucleus of the atom is also positively charged. Like charges repel each other, so the alpha particles are deflected away from the nucleus. Why did only a small fraction of the alpha particles show a slight deflection? Only a small fraction of the alpha particles showed a slight deflection in Rutherford's gold foil experiment because the nucleus of the gold atom is very small compared to the size of the atom as a whole. Most of the atom is empty space. Most of the alpha particles will pass through the atom without hitting the nucleus. Only rarely will an alpha particle pass close enough to the nucleus to be deflected. If the atom were a solid sphere, what would happen to the results of Rutherford's experiment? If the atom were a solid sphere, all of the alpha particles in Rutherford's experiment would have been deflected at large angles or even bounced back. Great work, students! Understanding Rutherford's gold foil experiment is a key step in learning about atomic structure. Stay tuned for our next lesson. Don't forget to like, share, and subscribe for more chemistry lessons. See you next time. Easy come from